This is very nice. Yeah. This is always wonderful to have another ERC grant. They are so competitive.
Yeah. It's a bit of luck as well, but here we are.
Of course, just like any of these grants, there's always a bit of a random noise in the process. But it's not pure noise, as you know. So.
Yeah, I hope so.
Yeah, of course.
We're all set.
Oh, very good. All right. So let's give people 1 or 2 minutes to stream in and then to join us, and then I'll make a few announcements before introducing our speaker today. All right, let's get started with the announcement. The first thing I wanted to do is to remind you of the events at the center in the coming weeks. On Fridays, there is no lunchtime talk because we have the third lecture in the annual lecture series, which will be given by Alan Love at 3:30 on the 10th floor of the Cathedral of Learning. Next week is Thanksgiving break, so we are taking a whole week off, nearly the end of the semester, but we have a week off. The next lunchtime talk will be on November 28th at noon at the center, and it will be given by one of our 2 postdoctoral fellows, Margarita Harris, and we invite you to come to this talk. Let me remind you that all the talks are also streamed at the same time. You can watch them on YouTube if you're not in Pittsburgh. 2 more announcements. The center is organizing a conference on science and values. Arnon Levy, our senior visiting fellow, is leading this conference. So deadline has been postponed from November 15 to November 30th. You can find more information about the call for paper on the center website, and we invite you to submit a call for proposal if you are interested in attending this conference. So November 30th is a new deadline for the call for papers. And the last announcement is that if you are interested in being a fellow at the center next year, or a postdoctoral fellow at the center next year, you still have time to submit an application. So deadline for both the postdoc and the visiting fellowship positions are December 10th. And you can find more information about the process online on the center's website. All right, that's it for the announcement. Now it's my great pleasure to introduce our speaker today, Adrian Wuthrich, who is a professor at the Technische was a professor at the Technische Universität Berlin of History and Philosophy of Modern Science. He specializes in history and philosophy of physics with an interest in particle physics. He obtained his PhD now in 2009. He's been at TU Berlin since 2012. He's been involved in 2 very important and quite influential research projects. One which some of you are probably aware of, the epistemology of the Large Hadron Collider, which was actually quite important. A lot of postdoc streams were involved in that project. A lot of researchers were involved in this project. And since 2002, he received a consolidator grant from the European Research Council, the ERC, for a project Network Epistemology in Practice. And I guess what we're going to be hearing about today is part of this ERC grant. It's one of the output of the ERC grant. So I'm really looking forward to your talk. Adrian was a visiting fellow at the center in 2011, 2012, I believe. So now more than a decade ago. Now we're looking forward to the day where you're going to join us again. So, you should keep that in your mind. We would love to have you back here at the center. And one last thing, if you're interested to know a bit about Adrian, you can go to the center webpage for all our former fellows who joined us back for these lectures. We are sending them a few questions about their interests, their memories at the center, so you can know a little bit more about Adrian on the center. All right, Adrian, the floor is yours. Thanks for joining us today.
Thank you very much for the invitation. Thank you very much. I'm very glad to be here. And indeed, I will talk to things related to my ERC project that was mentioned. It's strictly speaking not yet an output, but almost. It is actually what I like to call a pilot study to the ERC project, which is called Network Epistemology in Practice. I will start sharing the screen so that you can see, hopefully, the slides.
It works well.
Okay, I was just about to ask. So this seems to work. The title of the talk is Characterizing a Collaboration by its Communication Structure. So as I said, it's sort of a first attempt to go towards the things that you want to do in the project at a little bit larger scale. For this study, I had assistance by two students, Beate Federau and Michael Sichert, and the work was already done at the Technische Universität Berlin, as it is also the host of the Network Epistemology in Practice project. This, in fact, is, as I said, the larger framework of what I will be talking about today. It's what I will present is the pilot study to this project. The project is funded by the European Research Council, and it's hosted at the Technische Universität Berlin. And we're building up our team. Currently, we have already two people who joined in different statuses. Arno Simons is one of the postdocs, Michael Sichert, student member, and we're looking forward to hiring 1 or 2 members soon. So watch out for job ads if you're interested or know of any interested candidates. Let me give an outline of the talk for this evening here and lunchtime at your place in Pittsburgh. I will first again briefly mention the main research questions that we have in the larger project. I will then introduce the Atlas collaboration at CERN, which is the main case study of the pilot, example case of the pilot study, and we're also working towards more collaboration for the larger project. So I'll say a few words about the Atlas collaboration. I will then mention a precursor project in which we already were working with the Atlas collaboration and could collect a lot of interesting material, which forms the basis actually of the pilot study that I'm presenting today. The sort of the main part of the talk will be showing you the results from this study, which is on the one hand the Atlas communication network, how it looks like, and what its structure is. And I will also then spend some time on presenting the results that we got when determining the characteristic network measures of that communication structure of the Atlas collaboration. I will end with a brief summary. So coming back again to the larger framework of the main project, Network Epistemology in Practice, NEPI for short. In a way, the overarching question is, I don't know, a simple, in many ways simple and plausible one is how is in a large collaboration, such as these particle physics collaborations, how is knowledge formed and justified in a collective way? How do, in such a large collective, in such a large collaboration, how do ideas and hypotheses emerge? How do they diffuse in the collaboration? And how do the hypotheses or ideas evolve as they flow through the communication structure? And an important part of these research questions is also to ask what type of structure are epistemically successful? What type of structure seems to be conducive of epistemic success, not only in theory, but also in practice in a real world case as in Atlas, the collaboration at CERN. Methodologically, we focus not on published accounts, but on internal communication to a large extent. So the hope is that we get a perhaps more interesting picture of how these discoveries come about, rather than reconstructing them from the published accounts. Because this internal communication is mostly digital, not only since the corona pandemic, but already before, it's mostly digital, and it's usually a lot. There is a great deal of document and many messages exchanged, which will therefore not be apt for a close reading analysis unless you select very strongly. So we will appeal to methods from computational or digital humanities to be able to deal with these large amounts of interesting material. And some first steps, as I said, we have done some first steps into this direction in this pilot study that I'm presenting today. And it's done with communication data from the Atlas collaboration at CERN. And let me use this opportunity to really thank the Atlas management and the Atlas members for allowing me to do these studies. That's really great, and I appreciate that a lot. So let's move forward. So I talked a little bit about the main framework, overarching framework. And now let's focus on the case. The Atlas collaboration at CERN, many of you might know quite some things about it. I will give a very brief picture of what it's all about. Basically, it's located in my homeland, Switzerland, my country where I grew up. It's very nice, as you can see. And it's located on the French and Swiss border. What you can see here is not Atlas, not my case study, but the Large Hadron Collider at CERN, the particle physics laboratory. The red circle indicates where the accelerator, the Large Hadron Collider, is installed beneath the Earth, beneath the surface. And at some of these places that, I don't know if you can see this, there are some little circles, and at these places we have different experiments, mostly detectors that do experiments with the accelerated beams. And one of them is the Atlas experiment or the Atlas collaboration. So Atlas is one of the two bigger collaborations at CERN. The other is CMS, and there are a couple of other collaborations which do their experiments there. One of the big moments, among many others, that the Atlas collaboration had or will have was certainly the discovery in 2012 of the Higgs boson, that particle that the researchers were looking for quite a while, and they discovered it in 2012, and Atlas was one of the main discoverers of this particle. I have now a short video, which I'm not sure will work because we had some issues with the sound. Let me try it. It will only take 40 seconds, and I will try to give the sound from my cell phone. Let's see if we can get there. Otherwise, we will just then go to the next slide. So bear with me a moment.
The consistency everywhere between the ground scenario at the level at the level below plus or minus 2 seconds. So this distribution extremely clean, except one big spike here in this region here. So zooming in this region.
So you can tell me later whether it worked. The idea was to give you an impression of really also of the importance of this discovery. And by the way, let me know if you can hear me well or not, or if you can't hear me, then let me know. So the idea was to give you an impression of really this big moment. It was really important discovery, long awaited. And what we want to do in the project, and also to some extent in the pilot study, is going behind the scenes of such eureka moments and try to see how does this come about? How all these people sitting there in the auditorium, how could they do this, that they collectively discovered something like such an elusive particles? And certainly one way to reconstruct these discoveries is to have a look at their output, right? You just look what they publish, what the results are, and what they say that they have done. This is certainly an important way to do such studies, especially historical studies. But it is also quite well known that you have to be very careful, because these studies, these publications have the focus on presenting the results, and the way that they arrived at these results are often quite streamlined and do not necessarily reflect the actual discovery processes. So that's why in the network epistemology practice project, we attempt to rely less on these published accounts, but rather on unpublished internal communication. And I think this is quite original in some way, because this has not been done in many other cases. So much for the Atlas collaboration at CERN. Now let me briefly sketch the precursor project that we had at the University of Bern in Switzerland. Already then we had the support from the Atlas management to get some interesting insights into the internal communication of the Atlas collaboration. At that time, 10 years ago, we analyzed the material mostly by selective close reading. We were following the discussions and tried to zoom in where we had the impression that something interesting is going on. We found out, I would say, quite a lot. We could see how the internal review process works, and also how this internal review process, the knowledge about this process, was actually very important to make the collective results justified in a way that a single person could not have done. So I think this was a very interesting analysis, but it was still a selective reading. And now in the new project, one of the ideas that we can go for a comprehensive, if I don't know, complete, but almost complete analysis of the communication by using the digital tools that we have at hand nowadays, be it network analysis or also these more cutting edge things like the large language models, GPT or BERT and the like. Anyway, for tonight or for today, perhaps the important thing is that for the pilot study that I'm presenting, I was using the data that we have collected in this meta-atlas project. Here you can see a publication that we did at that time. It's in German, unfortunately, but perhaps you will find somebody. You will find a website to translate it if needed. But anyway, let's talk about that collection that I mentioned, the collection of documents, of messages from internal communication at Atlas. We basically could collect 24,000 messages from Atlas internal e-groups. It's a type of mailing list, and many of the messages that were exchanged on these channels were also relevant for the discovery process of the Higgs boson in 2012. What you can see in the plot is that the number of messages varied quite a lot over time, over the time window of our analysis. The mean was around 600 messages per month on all the lists, and it had the frequency has pronounced peak in June 2012, which is just a month before the Higgs discovery was announced in the video or in the seminar that you saw in the video. So this gives us perhaps some indication that the collection, it is certainly not complete, but it might be to some extent representative, because it shows this clear peak when there was really an important phase of research at CERN. The first and the last month we clipped from our analysis because for various reasons the data seemed incomplete and irregular. So the analysis focuses only on a smaller window that you can see in the plot. let me continue characterizing a little bit the collection of data that we had. We were analyzing the messages on these e-groups, on these mailing lists. In total, there were 175 such mailing lists. Here you see the top 15 in terms of number of messages. Again, here we see that not on all lists we had a similar amount of messages. Some had over 6,000 messages, others had much less. But we can see here in the top 15 of these active mailing lists, we basically have all the lists that were concerned with the analysis of the yet to be discovered Higgs boson. This you can guess from these abbreviations is Higgs H2WW. So these people were investigating the decay of the Higgs particle to 2W bosons and so on. So these were E-groups for people working together on different decay channels of the Higgs particle. Some of the other active lists were more concerned with determining background reactions, which is also very important to discover new particles. So you have to know the known particles very well in order to see whether there is something new. And we also have some more general lists, like that is with the label current physicists, for example, who are a list who is mostly used for announcements to all the members of the Atlas collaboration. So many types of lists, some more active and mostly concerned with Higgs analysis. Now, cases for comparison. The goal here in the pilot study is to characterize the Atlas collaboration by its communication structure. So we want to measure some characteristic quantities of the Atlas communication network. But let's say we find, oh, the density is 0.5. Then what does this mean? It's difficult to say. Is this dense or not so dense? So it's good to have cases for comparison. The problem is that, to my knowledge, there is as yet no such analysis of a scientific email collaboration, scientific in a stricter sense. So it was quite difficult to find some cases to compare. The best we could come up with for our purposes was one publication, which is not the most recent one. It's dated from 2002. And they analyzed a network, an email network at the University of Kiel in Germany. So this is in a way, it's a very general email network, but it might have some scientific aspect to it because it's placed at a university. But this is at least one study of email networks that we could take and compare our results to. We were looking for another case, perhaps a little bit more scientific. As I said, we could not really come up with the perfect example, but a good one is, I think, the Linux kernel developers. They have a mailing list archive, which is freely accessible on the internet, which does not mean that you can just do whatever you please with these data. So you have it's best to communicate with them and make you knowledgeable about the terms and conditions to use these messages. But we used this archive of mails by Linux kernel developers, so software developers. It's not completely scientific, but perhaps close to it. And we took the same year as the Higgs discovery, so 2012. Michael Zichert, the student assistant, did most of this work. He downloaded all the messages from 2012, which were about, let me see, 90,000 messages. No, sorry, 170,000 messages. And we then ran basically the same analysis as we did for the Atlas communication data. So the idea was really to have a comparison case so that we can then say, okay, yeah, really Atlas is dense relative to the Linux kernel mailing list. Good. One or two more words about methodology. The emails that we could collect in the MetaAtlas project got to us basically as any normal email would. We just used the normal email client to get the message, and then we could store the messages in an appropriate format. So nothing very fancy for the moment. We got these email messages, and the slide that I put here was also to perhaps remind you of two things. One is that emails, especially on lists, often have this thread structure that you probably know very well. So this was often the case, and actually the network that we constructed, as I will show you later, has some commonalities with such a thread structure. You will see that in a moment. The other thing that this slide may remind us is that these are internal messages which are not meant for the public, so protection of personal data and privacy is an important part in our project, and we're working with the Atlas collaboration closely to find the best ways to conduct such projects. This is the note on data protection. We really try to work out best practices for this type of projects. It's often a kind of a trade-off between all that we philosophers would like to know about the collaboration and the right of the people at CERN for their privacy. So we will try to find the best balance there. And we certainly take and implement appropriate technical and organizational measures to make sure that we do not violate any data protection laws, or also not some just moral principles that could come up in such a study. Well, so much for the methods. Let's move slowly to the results. How does that network look like, and how did we construct it? In a way, the network is just, one would think, a network of senders and receivers of messages, like we had also in the old days, Republic of Letters, for instance. But it's not quite that. We have a mailing list. So this means that basically the sender, that the receiver of all the messages is the list. So just making such a sender-receiver network would not be very interesting. So we have to add a little twist for constructing the network. We have to, as it were, cancel out the mailing list, make it disappear. The way we did that is that we connect two nodes in the network, two persons in the Atlas collaboration. When one person A replies to a message by B, which was sent to one of the mailing lists. So in the network, we see people connected. That means they have replied to each other's messages. This seems to be the best representation of a communication of which goes through a mailing list. So person A replies to a message sent to one of the mailing lists by person B, then they get connected in the network. That's why, in some sense, the network structure or the construction rule of the network follows these thread structures that you can often see in email clients. Okay, I spare you the details of all the nitty-gritty calculations that we had to do and all the calculations or algorithms that we ran on this network, on this data. What came out at the end was something like this. This is the Atlas E-group network as we reconstructed it from the data available. There are 749 nodes in total, representing Atlas members. And we had 5,591 edges, connections between them. This is not counting the weight of the edges. So if a person replies several times to another person, the connection, the edge between them will be weighted by the amount of message, by the number of messages that they send to each other. This is not counted here in this number. But in a lot of the following analysis, it will be counted, depending on the quantities that we use. 749 is about a quarter of all the active Atlas members, of all the Atlas authors of the publications. So this is also important to keep in mind. We don't see everybody of the Atlas collaboration here, only the quarter of them who was active on these mailing lists during the time that we analyzed this. And it goes without saying that people can, of course, work a lot in Atlas without sending these emails. The visualization follows a Force Atlas layout. Again, the details are not so important, but this layout is suitable for analyzing social network. In particular, it can show the substructures of the network, which are indicated here by the colors. The size of the nodes depends on the betweenness centrality of the nodes. This is an important measure in network theory. It basically tells us how many shortest paths go through one of the nodes, go through that particular node. So a node that is large here has many connections going through it, which is often a sign of a broken position in the network. So people who tend to bridge subgroups often have a high betweenness centrality in such an analysis. We spent actually quite some time to analyze the substructure. For lack of time, I won't go into the details in this talk. Just again show you the result that we arrived at. Basically, these subgroups correspond to the groups that were set up in the Atlas collaboration to make the different types of analysis of the Higgs decay. I mentioned that at the beginning. They had different mailing lists for discussing certain types of analysis of the Higgs decay, different decay channels. And in our analysis, we could basically reproduce this group structure. So again, these are the 5 major groups that were involved in the Higgs analysis. And what is that? Lila, purple group was the one that was, roughly speaking, concerned with calculating background reactions, which were important also for the discovery. So there is group structure. The discovery process is divided into smaller chunks of analysis. And at the end, we expect that these partial analyses are pulled together. We also put some effort in our analysis into seeing who is pulling the results together. Again, not going into the details, we could, with some combination of network measures, identify one node that you can see here in the network that is special in that it is a very active node, so replying or sending a lot of messages, and it does it in equal ways in almost in all the communities. So that was the characteristics that we were looking for. Who is the person that in this network has the position of writing a lot equally to all these important subgroups, because that might be the person who pulls the results together. And the result was actually quite satisfying, because indeed what it turned out that this person here, the orange one in the center, was indeed the Higgs, one of the 2 Higgs conveners at the time of the discovery, which means that he or she also had this official role of pulling the partial results together. So again, our methodology and our data seemed somehow working quite well, and also the data seems to be representative of what we want to do in our analysis. Okay, as I said, I won't tell you today the details of this part of the analysis. I would like to focus more on the characteristic quantities of the network. Which brings us back to the title of my project, but also to other very important work in philosophy of science, among others by Kevin Zollman, but many others have contributed to this branch, I would say, of philosophy of science, which is concerned with finding out, among other things, what communication structures are conducive for epistemic success. And one interesting result that sparkled my interest and was, I think, also quite a big part of the motivation behind my project. One interesting and counterintuitive result was that there are circumstances in which a very densely connected network, like the one that you can see here, is actually disadvantageous as far as epistemic success is concerned. So we may call this the Zollman effect, which was really a very nice result and taken up in the literature and discussed a lot. When does it obtain and so on? This is a very interesting debate. We don't have time, at least in the talk, for this. Perhaps you can take it up with the Q&A later. But I took this as a motivation for seeing, oh, wow, there could be something interesting going on. And my main question was then, does something like this happen in concrete cases, in real world cases? And because I already worked on the Atlas collaboration, the natural question to ask was, how does this look like in the Atlas collaboration? Are they a dense communication network or not? Do they show other characteristics that might be interesting from a network epistemological point of view? So in a way, I can characterize my project and also the pilot study by saying that I would like to bring to bear the network epistemological results to practical cases. One important distinction to have in mind when doing this transfer is certainly that the cases might not be exactly comparable. In my case, the Atlas collaboration, we have collaboration members, 3,000 in the case of Atlas, and which form a large group. And in the case of what I call here the sort of the Zollman case, implying many other studies, of course, we have a collective of members of a research field. This is sometimes called the scientific community. I don't want to use community here because I use this for the subgroups that I showed you before. So I hope not to mix up the terms. So on one side, you have collaboration members. On the other side, you have members of a research field, individual researchers or small teams. In both cases, I'd say in general, they have a common goal. They want to find out something. There is a problem, there's a puzzle. But in the Atlas collaboration, the efforts are usually much more coordinated than they are in just a research collective. And looking at literature in philosophy of science, one might say that in a collaboration, we have more a thing of a distributed cognition. So basically one big entity that does the research, and in that entity, the cognition processes are distributed, whereas in the case of a collective, we might call it more of a division of cognitive labor, as you know it from Philip Kitcher, for instance. Success in one case is a truly collective success in all the cases. Basically, either the collaboration discovers the particle or not. Whereas in a collective, in a research collective, we could also speak of success when at least one actor solved the puzzle. Then through consensus formation, we can also say that now the success is a collective one. So keeping these differences in mind, I still think that many of the interesting insights that came out of this network epistemology transfer to the case of a collaboration. For instance, one could imagine that something like the Zollman effect obtains when, in a very dense communication network in the Atlas collaboration, for instance, people adopt an erroneous result very early and then sort of get directed in a wrong direction. So I think similar things that we can see in the collective can also obtain in the collaboration. So what results did you get? For the following, it's important to have in mind that I'm trying to do, in a way, analysis of 2 points at the same time. I hope that is not confusing, but I'm sure you will bear with me. One thing is that I would like to determine and show you the results of this determination of the characteristic properties of the Atlas communication network with an eye on the Zollman effect. So density and clustering might be important. And at the same time, I would like to propose to interpret some of these measures as a measure for collaborativeness. So it's a little bit in parallel that I'm going through the next slides. And I hope to end up with perhaps at least slightly surprising finding. The first quantity that we measured was density. This is pretty much straightforward. Density is the measure for how dense the network is, so how many of the possible edges are really there in practice, in the concrete case. And I would propose to take this as a measure for collaborativeness. A collaboration, I submit, is the more collaborative, the denser its communication network is. If you talk to each other a lot, this seems to be collaborative. With an eye on the Zollman effect, this does not mean that it is necessarily a good thing. There are these cases where high density can be disadvantageous in epistemological terms. So what do we have in the Atlas case? We have 0.010. So 1% density, 1% of all the edges that could be there are actually there. And we find much smaller densities in our comparison cases. So on this measure, Atlas seems relatively collaborative. Let's go to another important measure, which has also some relevance in these effects discussed by Zollman and others, which is clustering coefficient and transitivity. I propose to take this again as a collaborative measure, as a measure of collaborativeness. A collaboration is the more collaborative, the higher the clustering coefficient of its communication network is. Again, in this network epistemology, we have the result that high clustering is not necessarily a good thing. Let me remind you, what is this clustering? It's basically a measure for how often is it the case that the friend of your friend is also your friend. So it's a measure for how many triangles do we have in a network. There are at least two variants, two ways of mathematically spell this out. One is called the global clustering coefficient, and the other one is the local one. And for Atlas, we find these numbers. For the network at the University of Kiel, we only have one number. And for our own rough and ready Linux analysis, we find these numbers. And again, turns out that Atlas is relatively clustered, and on this measure that I propose is relatively collaborative. Again, with a view on the network epistemological results, this is not necessarily a good thing. Let's rush forward. Degree distribution is another way of characterizing a network. The degree distribution, the degree of a node in a network is how many edges it has, how well connected it is. The degree distribution tells you how many nodes have a certain degree. So how many nodes have degree 1, how many nodes have degree 2, and so on. And the resulting, and you can get a distribution like this. That's the distribution that we got for the Atlas case. And it is quite common to try to model this distribution with a power law. You can see that a little bit better on a logarithmic scale. And why is it interesting to try to fit this with a power law? Because if it is a power law, one has some ideas of the mechanisms that could bring about this network. One famous example is citation patterns. It was found that they follow often a power law, and that you can explain them by so-called preferential attachment, which basically says if something is cited a lot already, then there is a tendency to cite it again. This is just to say that having a look at the degree distribution might give us some indication of the mechanisms that produced the network that we find. And there was also in network theory some interesting discussions of the properties of these power law distributions. Let me quote here one of the network theorists, Newman, who says the value tau of the parameter in the power law, the value tau equals 2, forms a dividing line between two fundamentally different behaviors of the network. For tau less than 2, the average properties of the network are dominated by the few individuals who have a large number of collaborators, whereas networks with tau larger than 2 are dominated by the little people, those with few collaborators. So this suggests, again, I think, quite compellingly, to take this as a measure for collaborativeness. Is it a network in which only the big guys are relevant, or do we have a network that is more sensitive to more silent voices, let's say? So I would propose that, again, we take this measure, this exponent, and whether if it's bigger than 2, we would have a more collaborative network than when it's smaller than 2. Alas, in our case, we did not manage yet to come to reasonable numbers. This is actually a notorious problem in the power law fitting of such degree distributions. There are quite some subtleties, and often the results depend a lot on the fitting procedure that you use, and which makes the results often quite unreliable. So that's why for the moment we just don't quote any values for this. But it would certainly be interesting to see what the value really is. And perhaps if we can analyze some more data of such collaborations, we might get a better picture of this aspect of the communication structures. There is another standard network measure which also has to do with degrees. It's called assortativity. Again, if you work with networks, you might be familiar with the term. Otherwise, let me say a few words about it. Assortativity by degree basically measures the tendency of people to, in my case, to reply to people when they have a similar amount of replies that they get. The idea is to measure something like this. Can we say that in the network, people mostly reply to those people who have a similar importance in this sense? So if I receive a lot of messages, do I then only reply to messages by people who also receive a lot of messages? So only, again, the idea is to see whether we can measure whether in the collaboration only the big guys talk to each other, or whether there is, again, more sensitiveness to also the more silent voices. One can spell this out in mathematical terms, and one can then determine the value for the degree to which this is the case. Since I'm not just interested in determining this value, but also interested in interpreting it as a measure for collaborativeness, I have to say 2 words of caution, or to give you some additional information. With this measure is special in the sense that it pulls in 2 directions. On the one hand, a collaboration with high assortativity in its communication network tends to separate members of different status. That's why I would call it non-collaborative. On the other hand, results from network theory show that if in a network we have a high assortativity, the dependence on individual nodes is quite high. So in an assortative network, if you remove nodes, it can easily happen that the network breaks apart. Sorry, I said this the wrong way. In a disassortative network, this can happen. In an assortative network, this does not happen. The assortative network is more stable. So in that sense, if the structure is assortative, the communication structure, this means that it's more stable, it's less dependent on individuals, and in that sense, you could call it more collaborative. So this measure goes in both ways. What do we find in Atlas? Well, we find almost neutral. We find 0.07, and we don't have values for the University of Kiel study, and we have our own value for the Linux kernel is also negative, but more negative than the one that we found in Atlas. So the charitable interpretation of this is Atlas just right? It's a measure that pulls in both directions, and we find a value close to 0. Why not? This is certainly something that we would like to investigate a bit more, but it could be that they have just the right degree of assortativeness. Be this as it may, our results so far show that Atlas is slightly disassortative. We have seen that it is quite dense. We have seen that it's quite clustered. And these properties, together with this slight disassortativeness, actually makes the Atlas network an unusual social network. This is what surprised us in the study, and which is also something that we want to investigate a bit further. This is a table. I don't know how well you can see this. The numbers might be a little bit small. This is a table taken from a textbook by the network theorist, again, Newman. It divides the different networks that he collected, sort of in a literature review. He divides them in biological, technological, and information networks and social network. The point here to take is that the social networks have, in general, positive assortativity. The only exception is a student dating platform, but which might be different for many other reasons. So in general, it holds that, let's say, scientific social networks like co-authorship networks have a positive assortativity. Atlas has a negative assortativity. And in a way, it's even more special because from network theoretic consideration, you can make an argument that show that actually, in most cases, if you have a clustered network and also some group structures, this leads almost automatically to an assortative network. And Atlas is clustered that has a group structure, as I showed you, but is not assortative. So this leads to the hypothesis that in Atlas there should be some mechanism at work that block this usual inference from clustering and group structure to assortativity. Again, charitable and I think also quite plausible interpretation is that Atlas might have implemented some measures who allow for the group structure, which they need to divide the cognitive labor, and which allows for this clustering so that the friend of your friend is also your friend, but at the same time avoid a strong assortativeness. So that was my final point of the results, and I come to the summary, if you like. I subjected a collection of internal e-group messages from the Atlas collaboration to a network analysis. I showed you that there is a quite pronounced group structure in it, which corresponds to the different analysis groups. I briefly mentioned that there is, I like to call it an octopus node, so a person who seems to be well placed to pull together the partial results. I then proceeded to show you some network quantities, and I proposed to interpret some of them as indicators of collaborativeness. On most of these measures, Atlas turned out to be collaborative, but perhaps not epistemically optimal in view of the results from theoretical network epistemology. And finally, Atlas is a atypical social network. It has a clear community structure and a high clustering, but is not assortative by degree, which might point to some special collaborative mechanisms that are at work there. If you would like to read more about this pilot study, you can go to the freshly published article in Synthese. It's a part of the topic collection, Digital Studies of Digital Science. Thank you for coming. Thank you for listening. I'm looking forward to questions and comments. Ist vorbei jetzt.